chemical equilibrium and LeChatelier's principle. Or if you want to be French, you can say LeChatelier. I, as always, have my lab coat on so I don't get holes in my shirt, and I got my lab goggles on for safety. I am choosing not to wear gloves. You can decide whether you would like to wear gloves or not. Nothing is ridiculously concentrated or toxic in this lab, though some things could certainly stain your skin. LeChatelier's principle is an interesting principle. It reminds me of the idea of inertia in physics, that an object at rest tends to stay at rest, an object in motion tends to stay in motion. Equilibria are ridiculously common types of reactions. When we introduce chemical reactions, we pretty much talk about reactants form products. And when one of the reactants or all of the reactants are used up, then we have products, and that's the end of the reaction. The reality is a little bit more complicated. It's kind of like when you eat food and breathe air and then exhale air and poop and pee out waste products, your body weight stays relatively constant. It's not the same particles that are making up your body all the time, but roughly the same amount of particles are in your body at any given time. A lot of reactions are like that. They don't start and then finish. They keep going and keep going and keep going. You have some reactants and you have some products when you're finished, quote, finished. In that type of situation, when you have a reaction that is going in both directions, reactants are forming products and products are forming reactants, if you perturb your equilibrium, the equilibrium will adjust to compensate. As a rule, if you add more reactants, you're going to produce more products. If you remove products, you're going to produce more products. Conversely, if you added more products, you would produce more reactant. If you removed a reactant, you would produce more reactants. Now, an interesting situation that we'll explore in part 3 of the lab can result when you have an exothermic or an endothermic reaction, where you can treat heat as a reactant, in which case yes, heat is a reactant in an endothermic reaction, and heat is a product in the other case, which is an exothermic reaction. So if you think of heat as a reactant, endothermic, product, exothermic, if you raise the temperature or lower the temperature, in either case, you're adding or removing a reactant or a product. And you can get the same kind of shift that we already discussed. If you remove a reactant, you're going to shift left, producing more reactants. If you remove product, you're going to shift right and produce more products. If you add a reactant, you're going to shift right and produce more products. If you add product, you're going to shift left and produce more reactants. So it doesn't matter whether it's an actual reactant or product or heat as a reactant or product. Your equilibrium, where you have some reactants and some products present and the reaction is going both ways, it hasn't that it's stopped, it's not stopped, the reaction is going both ways, then you can see this shift if you have something, say for example, that changes color. So, in part 1, the reaction of iron 3 and thiocyanate, we're going to place 50 milliliters of deionized water into a 100 milliliter beaker or a 150 milliliter beaker. I'm just going to rough eyeball it because it doesn't have to be exact, and I'm only going to add 40-ish, 50-ish milliliters of water into my 100 milliliter beaker. I'm going to add 10 drops of my iron nitrate, iron 3 nitrate solution. Ferric nitrate, old school name, iron 3 nitrate, 0.1 molar solution. 0.1 moles of iron nitrate per liter of solution. Adding 10 drops into my beaker. Cap up, as always. Nice, clean, new pipette. And we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Since my pipette was clean, I will put it back but we should, generally speaking, not put reactants back into their original containers. I will then also add 10 drops of 0.1 molar stock solution of, it says sodium thiocyanate. I don't have sodium thiocyanate with me today. I have potassium thiocyanate. Since our reaction is between the iron of the iron nitrate and the thiocyanate of the sodium thiocyanate, the potassium is not doing anything. It's a spectator ion, so I can use this instead. 10 drops of it as well. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10-ish. Swirl the mixture. Look at that, we got a little bit of a color change. From our original, we started slightly orangey brown, clear and colorless, and when we mix them together, we have this slightly darker orange than where we started. This is our reference solution. So I'm going to take some of it, and I'm going to put 10 drops of the reference solution into each test tube labeled A, B, C, and D. I have 4 test tubes here, labeled A, B, C, D. I have my solution, with a nice new pipette in it, and I'll put 10 drops of the reference solution into each test tube. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Should be enough for us to see. One, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Test tube B. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Test tube C. One more. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Test tube D. Test tube A is our reference. We're comparing our colors from test tube A and B and C and D as we add different things. Remember, in each of these we have just what we started with here. Iron 3 ion, nitrate anion, potassium cation, and thiocyanate, SCN minus anion. If we add a reactant, we should see a shift to the right. If we add a product, we should see a shift back to the left. Let's see what that looks like. So we're going to add more iron nitrate, more of our iron nitrate, to test tube B, and let's see what happens. Test tube B, more of our iron nitrate reactant. Pipette from before. One, 2, 3, 4, and 5. Here is test tube A. Here is test tube B that I added more iron nitrate to. Note what A looks like before anything was added. Note what B looks like after iron nitrate was added. That's your observation. Your conclusion should be, which way did the reaction shift? Right? In test to step number 6. Oh, sorry, that was step number 6. Step number 7, we're going to add the sodium, or in this case, potassium thiocyanate. We're going to add the other reactant to test tube C. Here we go. 4. 1, 2, 3, 4, 5. Test tube A, test tube B, test tube C. B and C look pretty darn similar. Maybe C is a little darker red. But certainly compared to test tube A, yellowish, test tube B, C, excuse me, is more reddish orange. Step number 8. We're going to add some sodium nitrate to it. Sodium nitrate, also 0.1 molar. So we have roughly the same concentrations each time of our reactants or products. Now if I add potassium thiocyanate and iron 3 nitrate, sodium nitrate, we'll have to just pretend that this is potassium nitrate, is one of our products. So we're pretending that this is potassium nitrate. Let's see if it works. Five drops. 1, 2, 3, 4, and 5. What do you think compared to test tube A? Test tube A, yellowish orange. Test tube D, light yellow. So it went from here and got lighter when we added the, quote, potassium nitrate. When we added either of our two reactants, it got darker. Test tube A, test tubes B and C. Test tube A, reference solution. Test tube B, adding a reactant. Test tube C, adding a reactant. Test tube D, adding a product. Which way did the reaction shift? What is your observation? That's the end of part 1. The part 2 equilibrium reaction uses a reaction that involves complex ion chemistry. Now, I didn't learn complex ion chemistry until at least my senior year, if not graduate school. So the exact chemistry involved isn't what's important. What is important is that blue copper 2 sulfate ions change color in the presence of ammonia. And so we'll see what happens when copper 2 and ammonia get mixed. We can remove ammonia by adding hydrochloric acid. And so we'll see the color change in the presence of ammonia and in the removal of ammonia and what it starts as without ammonia. So in part 2, we're taking 10 drops of 0.1 molar copper sulfate and putting it into a new test tube. 2, 3, 4, 5, 6, 7, 8, 9, 10 or so. Light blue. We will then add until we get from this sort of lightish blue to a deep, deep royal blue. New pipette. We'll record the number of drops just so that we have some data on our data sheet. Here we go. So 1 drop, it got darker, but it's still not, I would say, not royal blue. 2 drops, 3 drops, 4 drops. It's looking a little cloudy now because of some complex ion chemistry that's occurring. 5 drops, 6 drops. Oops, it's getting a little darker. 7 drops. Starting to see the dark, dark royal blue. 8 drops, 9 drops, 10 drops. Oh, that's a nice royal blue. 1 more for good measure. 11 drops. 1 more. 12 drops. Really nice royal blue. Okay? $11 drops or 12 drops, whatever I say. We're recording on our data sheet to turn our turquoise blue a royal blue. Now, this is 1 molar ammonia. We're going to add 1 molar hydrochloric acid to it. Same concentration. Royal blue, copper in the presence of ammonia. Let's remove the ammonia. Removing a reactant. 1, 2, 3, 4, 5, 6. Totally disappeared. Color. 7, 8. Remember 7. I think we'll see if there's any change more. 9, 10, 11, 12. Wasn't really any further change after 7 drops. So 7 drops seems to have brought us right back to, roughly, our original starting color. It's just this is getting dilute, so it looks lighter in color, but it is, of course, the same blue. It's just been diluted. So when we add ammonia, it got royal blue after it went through a little cloudy phase due to some complex ion chemistry we need not worry about. When we removed our ammonia, it seemed to have gone back to just our regular copper 2 ion color, because copper 2 sulfate, the sulfate is not complexing with the copper, and it's just, this is the color that copper 2 ions are in solution. When they get complex with the ammonia, it gets royal blue. If we remove the ammonia, we seem to go back to where we started. So I leave it to you to discuss with your instructor and write in your conclusion column, which way is the equilibrium shifting when we add hydrochloric acid? When we remove our reactant? I'll let you see it again. When you add ammonia to the copper, light blue copper ion, it turns first cloudy and then a royal blue. When we remove that ammonia, kind of giving away the answer, but when we remove that ammonia by adding acid, we can swirl it as I add it, go back through our cloudy to our light blue. Section 3 involves more complex ion chemistry that we're not going to really go into, but a solution of cobalt chloride in dilute hydrochloric acid. So this is 0.09 molar cobalt chloride in 2.6 molar hydrochloric acid. It's so that we have just the right amounts of reactants and products present for this endothermic reaction. Cobalt complex with water in the presence of extra chloride and heat goes from pink to a purple blue. It makes the waters come off of the cobalt ion and the chlorides go on. So cobalt chloride is purple blue. Cobalt without chloride associated with it and associated with waters instead is pink. And so we're going to prepare 3 different test tubes, one at room temperature, one hot, and one cold. All right? For part 3. So it says take 20 drops of this stock solution and put it into 3 tubes labeled E and F and G. So let's do that. Drops or so, roughly a milliliter. So we'll do a squirt into E, a squirt into F, and a squirt into G. I have a ice water slush bath set up, and I have a hot plate heating some water. And it says to observe and record the initial color of all 3 test tubes. And there you go. They're all this light pink color. All right, and I'm going to get a temperature probe just for the sake of argument. We don't really need data points for what the temperature is, but we definitely want to at least know for certain, how cold is this water, how hot is this water, so that we, know that the cold is cold and the hot is hot. That the cold water is colder than the hot water. All right, so our cold water is roughly, let's see, ice temperature, not too much of a surprise, around 1 degree Celsius, maybe a little colder if we give it some time to equilibrate. I didn't put any salt in there, so we shouldn't go below 0. All right, so our ice water bath is definitely icy, just a hair above freezing. Our hot water, on the other hand, says to go for 90 degrees. It's not going to really matter too much. If we're over that, we don't want to be too much under that, but we do have a huge difference in temperature. We're only at 50 degrees so far, so maybe I will crank my hot plate up a little more until we can get it a little bit hotter. Again, making sure that I don't melt my cord onto the hot plate. Reference tube. Ice bath. We'll let that thing cool. And even though it's not up to anywhere near 90 degrees yet, we're at 52 degrees, we will hot that one. And then we'll compare. We could put our temperature probe directly into our test tubes, but as long as we give them time to equilibrate, we can be confident that our reference is definitely hotter than our ice, and our hot water is definitely hotter than our room temperature, which in turn, of course, was hotter than our ice. Remember, heat is a reactant. So if I remove a reactant, if I lower the temperature, removing heat, looking at the reaction on page 121, the cold one seems to be a lighter pink than our room temperature. Ice bath made this lighter color pink. Observation. Our hot water is currently at 60 degrees. I need to wait for it to warm a little more. Let's see if we can see anything even at 60 degrees. Careful not to burn myself. Our hot one seems to be a bit darker than our room temperature one, but we'll leave it in there a little longer. You will get to enjoy the time lapse. I will have to sit here and wait for my water to increase in temperature. So our water is up to 98, 99 degrees, plenty hot. Room temperature. When heated, look at that, purple. When heat is added, when the reactant is added, we shift to the copper with no waters attached but chlorides instead, and it's purple, as opposed to the ice, here we go, put it in order, which is a lighter pink than the room temperature. Frost off of it, right? Cold on the left, light pink. Room temperature in the middle, sort of an orangey pink. Purple when heated. Heat is a reactant in this reaction, going from copper with water associated with it to copper with chlorides associated with it. Purple. That's the end of experiment 15, LeChatelier's principle. Not like the physics, an object at rest tends to stay at rest, but instead an equilibrium, forward reaction happening at the same time as a reverse reaction happening. An equilibrium when stressed will shift so as to minimize the stress. Add a reactant, remove a product, shift right. Remove a reactant, add a product, shift left. Even if that reactant or product is heat, it still works. Hope you enjoyed.